Well, welcome back everyone so far. We're just running the clock and we'll get started. Well, it's time. Welcome back everyone. I hope you all had a restful holiday or catch-up day, as it pretty much was for me. We're just about at the end of week 6 already, and our goal today is to get through section 3.3. Won't take long. We just left the last problem over the weekend. We didn't want to rush through that one. I think it was one to do very carefully. Then after we complete that section, we're going to move over to predicate logic as opposed to propositional logic. Part of our goal here is to say, what is the difference between the two? And then at the same time in this section, we'll introduce the universal quantifier. It's a upside down A is a symbol, and it's read as for all. We'll often say for all X, some property happens. We'll also introduce the existential quantifier. It's a backwards E, but in a different sense backwards. This one is just saying there exists or for some X. So those will be interesting topics. And in 3.5, we'll have to deal with nested quantifiers. Well, any questions at all, folks, before we get started? Oh, a thought did occur to me. We did have an exam as well. So for the folks who took the exam at a testing center, check your ISU email address if you haven't seen your exam just yet. I emailed everyone your graded exam back to your ISU email address. If you took the exam in the classroom, then I have the hard copies down here. But if I don't see you on a regular basis and you want your exam back sooner, don't hesitate to just reach out. We can send a simple email or a message through Moodle, which just is a convenient way to send an email. You could say something simply, Mike, could I get my exam back? That will be just fine with me. I'll be scanning exams, getting them returned as well on probably Friday when I start grading for the week. Also, I do have the solutions posted here, but I did have one student with a valid reason to make up the exam late in the week. So I'm going to unhide this once all the exams have been taken, just to protect the integrity of that exam there. I think that is actually the end of my announcements, though. Any questions at all, folks, before we get started? Okay, well, we're going to be done with chapter 3 when we return back next week. And as we go through the weeks, we'll have midterm week to come through. There won't be any special project. There's no exam. Exam 2 is going to be this week here. So all I'm doing on midterm week is just reporting your grade as it stands on the Friday, the end of this week here. So that will be your midterm grade. So after that, looks like we have exam 3 right before close week, which is just a big review week for us, review catch-up week. And then we're just about at the very end. Well, we're almost at the halfway mark. So with where we're at so far, here's the section that we left from before. I did have to put a revision on this one, and I added the revision to the blank documents at the top of the Moodle website. The revision, let's talk about it right away, is I said P implies P. Clearly a mistake. It was invisible to my eye at the time. P and Q sometimes look similar. Should have said P implies Q is logically equivalent to its contrapositive, not Q implies not P. So that's an important one right there. That's not one you really want to mess up. Sorry for the typo. Aside from that, just a quick refresher on what we're doing in this section. We're looking into propositions, and we have now a real trichotomy. A proposition can either be satisfiable, which means it's true under at least one truth assignment. I guess it's not a true trichotomy. There's overlap. It's a tautology if it's true under every truth assignment. And we say it's unsatisfiable if there is no way to get a true out of it, no matter how you assign the truth values to your P's or Q's. The bigger thing we want to talk about was really logical equivalence through the tautology. So first, We say this was a tautology because when we look at the truth table, we have all truths. Then next, we said that this one right here is satisfiable because sometimes P and Q or P and not Q is true, just depends on the truth table. It can't be a tautology due to at least one false occurring. This one is kind of a wacky statement altogether. When we looked at this one really carefully, we saw that there's no way to get a true assignment for the overall statement over when we put it all together. So we called this one unsatisfiable. Then this was really, in my view, probably the larger concept we want to talk about in this section, logical equivalence. We check logical equivalence by looking into the truth table. Say, for example, we were looking to P implies Q, not P implies not Q, the contrapositive. We have an overlap on truth assignments. These truth assignments here match these. So what that tells us is we have logical equivalence. This side will always be true simultaneously as this side, and vice versa. This side will always be false simultaneously at that side. And logical equivalence is a powerful way to think about these logical connectives, because now it allows us to do a kind of algebra with these sort of things. Let's zoom in on this a little bit more. We have the De Morgan's laws. These come up a lot. In section 3.2, it came up as well. It tells us if we negate either a conjunctive or a disjunctive, the and or, we get this property. Notice that we negate both P and Q, but the and here flips to or, and vice versa, the or on this one flips to and. These actually will come back when we go to the universal and existential quantifiers in just the very next section. And lots of other weird properties like the distributive property we double checked as well. So in showing something is logically equivalent, again, we're just matching up the truth assignments. And this is the one that we left off for after the weekend. We did the hard work of just filling out this portion right here, the P, Q, and R. We have 2 different assignments for all of these propositions here. And so that means there's 8 combinations altogether. But I encourage you to find a systematic way to write them down. It doesn't have to be my way, so that you're not worried too much about getting it just right in an exam setting. It is possible to have a problem just like this one in an exam situation. Now, next thing we're going to check is, let's see here. We put down Q or R, P and Q or R, and we're trying to determine logical equivalence between the one in blue and this one in green. But we could do a lot of mental assignments of truth values to try to check this one. A good idea here is, let's break it down. Just like how we have Q or R here, we're going to look at this one all together. Let's first take a look into P and Q. Then we'll take a look into this one, P and R. Then once we have truth assignments here, it's a lot easier to put in the overall truth assignments to the larger portion, P and Q, or P and R. So when we go to check for logical equivalence, we're trying to see if the truth assignments here are identical to the truth assignments here. Well, that's the setup so far. We saved about a few minutes just jumping back to this spot. Any questions at the moment, folks, before we give this one a try? Okay, well, first thing you might want to take a look into when doing these is pull up section 3.2. Scroll down to about right here. These are really great for note cards, by the way, and have these pulled up as you go to visualize the truth assignments we're about to put in. For the or, our author calls this the disjunctive one a lot. There's really only one way to get a false here. Both Q and R have to be false. So running through both those columns, I'm just going to find the falses and then flip everything else to true. So this line right here, false and false with an or, would give us a false. And this other line, these are the only 2 ways to potentially get a false for Q or R. Everything else has a true one way or another, either for R or F. And with the or, that assigns true to everything else then. So TTT, false, true, false, true. So that's one down. The purpose of this one here is now we can fill out the truth assignment for one major part of the equivalence we're checking. I'm going to use the yellow highlighter just to kind of indicate where my eyeballs are looking as we fill out this one. We want to be looking at column P, as well as column Q or R that we just filled in. This time it's an and. So this one is going to be the one that's mostly false. Let's identify the truths. That's when both true occurs. Well, yeah, there's fewer truths than falses, I'd say, on this one. We'll have a true here, a true again on this one. Now, let's find any other truths we can see. This one would evaluate to true. With the and operator in the middle, we just needed true and true to line up to make the whole overall statement here true. And the rest of them have opposite assignments, which automatically says false on every single remaining cell. So that settles this column. The left-hand side of this logical equivalence is now done. The rest of the work is just to get and attack the right-hand side here. Any questions or comments at the moment to this stage? Weird kind of math, wouldn't you say? I think it's kind of fun and relaxing in a way, but it's definitely, first time I saw this, it just didn't even feel like I was in a math class any longer whatsoever. And that's all right. Mathematics is just applied logic, really. So we're in kind of an unusual spot when we do these kinds of things versus an ordinary math class. So let's fill out these two operators here and here with the and. For this one, we're just doing P and Q, so first two columns. And same strategy, I'm just going to look for the truths. We have double true here, so true on that one. And skipped past this one. True as well. Everything else ought to be false. Then we just do it all over again. P and R this time. So let's change our focus to the entire column P. Let's make this a big highlighter. And the entire column R. So for P and R, line up, find out where the truths are. So true here, and it should be remaining false. It's always a good idea to scan through and double check because sometimes our eyes can be deceiving on this. But yeah, it looks like that's the only truths on this column here. So drop in false everywhere else. This is the type of work, by the way, where you're technically a little bit faster if you go a little bit slower, because there's lots to consider on this. Now we're on the big right-hand side of the logical equivalence. We have P and Q here, P and R right here. There's an or in the middle, so all we need to take a look at is on those two bits there, when is it double false? That's going to lead to a false on the or operator. So here we would get a false. Looks like lots of falses. Here, then the row below, then two more. Bottom two would evaluate to false, false as well. Now, because it's an or operator, anything that has a true, even double truths, is just going to evaluate to true overall. So true here, and true here. I think the truths would have been faster to find, but we've got it, folks. That's the whole truth assignment. Now for the big part, logical equivalence, all we check is this column. True maps to true to true, false to false, false to false, false to false, and I forgot to say, also checking this column. Looks like no matter where we are on this, we have exact the same logical assignments. So we just say, overall, the statements are logically equivalent. This is a kind of a tricky problem in a certain sense because one word of warning is we do have to put down a conclusion some way, somehow. You could just rewrite this and say this whole thing is logically equivalent. Maybe just point an arrow at it. That'd be just fine. I think the best way to say that is that, therefore, P and Q or R is logically equivalent to P and Q or P and R. So we have a conclusion down below. Or again, you can just say point arrows and say logically equivalent That's okay with me as well. If you clearly express your conclusion and anybody reading it can tell what you mean, then that's good enough for me with this kind of stuff. It's good to write out this way as well, because just the process of writing it out, say the operators as you do this, and it's going to really connect in your mind that this is an and, not an or, and that this one's an or, not an and so on. It just makes this, the learning and remembering of this kind of stuff, a lot more straightforward. Well, we did it, folks. That's the end of section 3.3. Glad we took our time with it. That took us about 14 minutes out. Any questions at all getting through this one? Okay, so we're picking up a lot of tools with logic so far. We haven't really used it for any great leverage. We haven't solved any problems doing any proofs. We haven't done any induction proofs, anything like that. But we're getting pretty close to that. If you go into section 3.4, some of the reading here in section 3.4 is a little bit difficult than the other reading. So in section 3.4, we're going to introduce predicate logic. But as far as the reading goes, you'll get into a subsection talking about proofs. If you decide to kind of skim over that, that'd be okay. That's something we are going to circle back into and cover in a very, very strong way. There's a couple kind of preview topics in that reading that I think are difficult as they're sort of disconnected, but they're preview topics. In the section notes 3.4, these are the actual main topics that we're going to be examined on in the second exam. And this is one of those weird sections where introducing these quantifiers is really important in logic, but it's curious that in the book, I do like this book, I don't like the exercises. The book itself, the reading, talks a lot about examples working with these, but all of the exercises are really, really advanced exercises. They're not bad, but they're not the exercises you would assign to a person seeing these for the very first time. So our book is starting to look like a great intro book for the reading section, a really, really rough book for the exercises. So occasionally we'll have the exercises as a PDF document down here. So click on assignment 3.4 and it reveals these are the sort of problems that you'd want to do when you're learning these kind of operators for the very first time. Some of them do get a little bit more advanced toward the bottoms here, but we'll cover just how exactly each one of these goes through these lecture notes. So there they are. So welcome to section 3.4, predicate logic this time. So if you're really familiar with English, you might have a good indication of why we call this a predicate versus a proposition. But let's take a look and view on both of them at once. First definition 2.1 from the first day in class makes an appearance. It's just relevant here. A Boolean value is just a value that's either true or false. Review information from section 3.2 definition 3.1 is that a proposition is simply a statement that is either true or false. Then finally, here comes a predicate. Predicates are a little bit different. They say a predicate P is a function. Other textbooks call predicates propositional functions. So if you read it that way before, we're talking about the same thing with this slightly smaller wording, predicate. It's a function that's going to assign a value, or true or false, to each element of a set U. So it truly is a real function in and of itself. That is, it maps a set U, think the set U as being the universe of discourse, or domain of discourse, or just simply the universe, same as in set theory. The range, well, yes, the range and the codomain is just going to be true or false. And we call the set U, I think we said that already, the universe. And we sometimes say P is a predicate over U. I don't know if that wording comes up a lot, but the author thought it was important to mention. So that's what's going on so far with predicate logic. We have a function that's going to depend on something inside here. The set U could be a set of numbers, it could be a set of people, anything whatsoever. So with those definitions down, all we're doing in example 1 is nothing too major. We want to determine which statements are propositions and which ones are predicates. Well, let's start with the first one. 5 by 2 equals 4. If you're looking at that and feeling like that's weird, it's automatically false. that means you're looking at a proposition right away. On this one, 5 by x equals 4, well, you can't really assign truth or false to that, right? This one depends. It depends on what is x, what is its value. We might also want to know what are the set of x's that are relevant. In other words, what is the universe that we're dealing with? I think our author most often says, what is the domain or domain of discourse? So telling the difference could just be simply saying, this is a proposition. Since this is false, and the falsity does not depend on any element in U. In other words, there's just no domain of discourse here. This is just a straightforward statement, either true or false. But this one is different, right? It's sometimes true, sometimes false. We would call that a conditional equation, much like a conditional proposition. Here, we would say that this one is a predicate. Since for this one, it's truth or falsity depends on x in, well, it never said what the domain of discourse was. We can imagine what it ought to be. Maybe it's a small set like Q, the set of rational numbers. The solution here is a rational number, so that feels appropriate. It's highly content sensitive. Sometimes it would just have to be written in. Other times, if you just said X and R, we're selecting a pretty large domain of discourse. But it would fit this problem right here because, again, the solution is an element in R, and that would work out just fine. So what makes this a predicate is this is really infinitely many different statements like this one. They all depend upon X. And so we can say the predicate is, or the proposition here, well, let me say it better. The predicate here, it's not great to get those words mixed up, is P of X. It becomes a statement, X, 5x equals 4. And it maps from R to the set of Boolean values, true, false. That's a lot to say about this kind of equation. This is an equation you probably saw in elementary school, for example, but lots going on here once we go from a proposition to a predicate. Any questions at all, folks, on looking at the difference between those definitions? Oh, sorry, I'm trying to fix my window here. Okay, well, with that out of the way, let's look into some other kind of predicates. In example 2, we've defined a new predicate function, P of n. N squared plus 2n is an odd integer. So this whole right-hand side here is much like the 5x equals 4 when we wrote out this predicate function. The domain of discourse is the positive integers. Let me zoom in on that. This really just show that superscript. So z, well, maybe said it a better way. This is not just the positive integers. This is all integers larger than or equal to 1. We're finding values of n for which the predicate P of n is true and for which the predicate P of n is false, which means lots of examples you could give to this. But that's just kind of launching off what the idea is over here. This is a predicate statement because it's sometimes true, sometimes false. And, well, I'm not too sure what would work here for getting true or false. Sometimes you could just play around with the predicate function and just see what happens. So evaluate P at 1. P at 1 is going to be this entire statement right here. It becomes an actual proposition once we pass a value to n. The proposition is now that 1 squared plus 2n, let me try again, 1 squared plus 2 times 1, which will be equal to 3, is an odd integer. Well, looking at that, we can definitely say this is true. So when we go to evaluate P at 1, the output would be true altogether. So at n equals 1, P at 1 equals true. Equals true in the sense that the predicate function is mapping to this as its now range. So we have a value that made the predicate true, and we want to find a value that's going to make it false. Again, no idea what it is. Let's just hope P of 2 works out. You could get really fancy here, plug in P of 100, P of, let's say, not P of 0, because that would be out of domain. Let's try just P of 2. Watch out for those little values right here. Sometimes that can really make the difference in some of these problems. So P of 2 becomes the statement that 2 squared plus 2 times 2, that's just a fancy way to say 8, is an odd integer. Well, we know 8 to be even in its parity, so there wasn't necessarily anything wrong with the statement. This is a statement that's either true or false once we pass a value of n. It just happens to now evaluate to false. So we can say at n equals 2, P at 2 evaluates to false. So that's us working with just the predicate function, trying to get a better feel for what are we saying here. P is a predicate over a domain U. The domain of discourse was this, z greater than or equal to 1. So all integers equal to 1 or larger. It outputs a value to true or false as a function. And so we get to literally say P at 2 equals false, much like you might have said f of x equals 3, and P of 1 equals true. Well, any questions, folks, on getting through that one? Okay. Well, with like a lot of things we've discovered in these books, there's a lot of tiny little details that we have to consider. But usually the hardest part is just introducing the topic. Once you get a feel for how things fit together, it becomes a lot easier to work with these kinds of things. This function right here took just one input. This one takes 2 inputs. Sometimes we might call this a binary function because of the 2 inputs that are going in. That means the domain of discourse this time is, well, x and y looks like they're going to be numbers, but we have to use R2 now since we're taking values that come from x, different values. Let me try again. Value x comes from R, a different value y comes from R. So our whole domain is now R2. This time we just want to find values x and y, for which q of xy is true, for which q of xy is false, same problem as above. And the statement this time is that q of xy is the statement that x plus y is 10. Like before, we can just plug in values and try to get an output out. But if the domain is R2, we probably don't want to grab things randomly. Let's just try to make things fit. Let's go for a true right away. So at x equals y equals q of xy will either be true or false, but let's take a look in the right, q of xy, what the statement would be. First, we have to find some x's and y's. We're trying to force a true on this one. Any volunteers from the class on what combination could work? Kind of a weird math problem because this is one of those problems where infinitely many correct answers on this one. But you know what I would do? I would probably go like this. 0 for x, 10 for y, because I'm trying to make this statement true. So now if I evaluate q of xy, let me plug in the values. At 0, 10, we just get 0 plus 10 equals 10. This evaluates to true. And if we'd like to say it over here in a slightly different way, that means qxy, I forgot the y on this one, forget it's 2 inputs, x is 0, y is 10, itself evaluates to true. So that's our first go at this. Now we need to make one come out at false. So let's say at x equals, oh, I didn't want to put a value in. At x equals and at y equals, we need two values so that when we pass it to this predicate function, this, which will turn into a proposition, must be forced to false. Any volunteers to make something absolutely false on this one?
You do 3 and 9 to make it false.
Absolutely. Let's go 3 and 9. These are always weird because there's as many correct answers to forcing false as there is people in the class that could come out. There are infinitely many more. So it's one of those weird problems where it's kind of hard to start. But thanks for supplying those values. At 0 and 3, let me just fix that 10 there. The predicate 3, 9 becomes the statement. I want to put colons on this one. This becomes the statement that 3 plus 9 now is equal to 10. We take a look at that and we see we're staring at a false right away. And then this implies Q, 3 comma 9, evaluates as a function with two inputs, two arguments. This function is itself now false. So we did it, folks. In both cases, we found values that made the predicate statement, the large statement here, either true or false. And I was being pretty picky on how I was writing these out. I'm not super picky on how I'm grading them, but I wanted to put colons here because here I'm just saying what is the actual proposition associated with the predicate function at those values. I found the value here. Then we can say, as a function mapping, Q goes from R2 onto true false. I'll just abbreviate TNF. And so because the mapping takes on this form, this is the way we'd actually say Q equals. We have to say one of the values in the range. So Q010 is true, Q39 false. Well, we did, folks. Both of these functions are ordinary functions in their own right, but this is how we sometimes view them, as just a statement that depends on either inputs or an input. So a predicate function just implies loads of propositional functions that tie to it. We just vary over the variables. So that's our introduction so far. We're going to try out a few neat things, just getting used to this new kind of logic. As well, introduce the quantifiers. Any questions whatsoever with predicate versus proposition? Okay, so on to the next topic. The quantifiers. These usually are the rough patch in getting through a logic course. This is probably the rough patch in chapter 3. If not this section, then maybe the next one when we look into nested quantifiers. So this is a good one to go carefully. Good section to read in the book multiple times to get the real feel for this. And let's give it our try for our first go. First, it's the universal quantifier we'll take a look at. When you just hear the words universal quantifier, think the symbol that and read it out as for all. So a universal quantifier, first, we need a predicate over S. I guess our author does use that verbiage a lot. S is the domain of discourse. U and the other problems. So now once we have a predicate, S could be R, it could be R2 in the last problems. We have a proposition that goes like this. Read out that upside down A as for all elements X in the set S. We have some predicate statement, P of X. And the whole statement here will be true if for every possible assignment, or excuse me, element X in S, that domain of discourse, we have that this comes out as true altogether, the predicate. So that's what gives us a universal quantifier. But reading that, our author has a really great remark that Wasn't super emphasized in the reading, so I thought let's emphasize it here. You can think of these quantifiers, this one first, as, this is his wording, a supersized version of the and operator, the conjunctive. So in other words, if you say for all x in x, x in s, p of x, that's no too different than saying, here are all your x's, let's just list them out. For all x in that set, p of x would be logically equivalent to p of x1 and p of x2 and p of x3, so on, all the way to p of xn. And we know that this is true if and only if p of xi is true for all I. The statement is longer than I thought it was going to be. I is the subscript, so I has to range from 1 up to n. But that's just because of the n's right here. Back up to the ordinary statement. For all x and x, p of x, this has to be true if p of x is always true for every element x in that set S, the domain of discourse. But visualizing it this way, you're just connecting loads of ands, potentially infinitely many different ands all at once, is a really great analogy to tie back what we were doing in just the last two sections. So that's the universal quantifier. And when you see that upside down A, it's kind of weird. Think and say in your mind, for all. The for all here is because it's true if and only if for all of those now propositions, they have to come out as true, whereas that's the predicate on the left. Any questions, folks, with the universal quantifier? Okay, so next is the existential quantifier. The names always seem curious the first time you read these things, but the names are actually really well chosen. Existential quantifier, we write down the symbol backwards E, different kinds of ways to write down these symbols. So whenever you see existential come up, this is the symbol, and think of, well, lots of things you could say. It's in a certain sense the opposite of for all, but it's not saying none, it's saying for some. Or you could be saying at least one. Let me say this a better way. You could read this out as for some, or you could say at least one. So that's different ways to visualize what the existential quantifier is saying. If this symbol is for all, the existential quantifier says there exists at least one element in the domain of discourse for which the proposition P of X is true. So take a predicate P over S. S is just, again, the domain of discourse. Writing down this says there exists at least one X in the domain of discourse, S of X, for which P of X is true. Then when we look at this entire statement, this statement is going to evaluate to true if at least one X occurs. That gives us P of X as a true statement. If that happens, it doesn't matter how ridiculous the rest of the statements are for the other values of X, this would become overall true. And we're in the same situation for the OR operators. We mentioned if you have something that's true here, it doesn't matter how ridiculous, how patently false everything else is. One truth, when you're connected through ORs, makes the entire overall statement true. So that's why we say for some, one of them's got to be true at least. So sometimes we say at least one whenever that quantifier comes up. And just another reminder here for parallelism, this is true if and only if P of xi is true for at least did not think I had enough on that space. At least one I between n and one. And then one is just referring to the subscripting from here to here. So one truth here means the whole statement here would be true. Whereas up here, one false means the whole thing is false as well. Really think of quantifiers as extending the and operator, the or operator, and that's a really great way to visualize this kind of new information. Any questions so far, folks, looking at both of them? Both quantifiers, rather. Okay, other terminology that does come up in this section is when we refer to the variable x, right here, we think of that as a free variable. The idea is, here in the parenthetical, x is free to roam across any element in the set S whatsoever. But when x comes up here, next to the existential quantifier, or here next to the universal one, we think of it as a bound variable in that case. So x can't be moved around in a certain sense. We think of it as bound what's in that position. Well, if you've taken linear algebra, calling x here a free variable is not the same in the linear algebra sense. The linear algebra sense, that was more about pivot columns and all that kind of stuff. So I find this kind of strange verbiage in a certain sense, but it does fit in this context to say it that way. Well, that's a lot of talking about the brand new operators here, the quantifiers. Next thing we want to do is just practice working with them. For the organization of the notes, this is going to parallel quite a bit what we did in section 3.2. We're going to determine statements are true or false. We're going to express certain statements in terms of quantifiers. What else are we going to do? Next, we'll do some translations where we want to read out if a statement is already formalized like this. What does it say exactly? After that, we'll try to reverse it. Oftentimes, this is the harder one, going backwards from this information because we're translating ordinary text, which is imprecise, to logical statements. Then finally, this table is kind of like the dual to the table we saw in section 3.3 with logical equivalence. Notice that De Morgan's laws are still here because it affects ands and ors. And this is what happens. If you negate an universal quantifier, turns into an existential quantifier, and you also negate the predicate inside that statement. So we'll come back to this, work on a few more problems, but really this is kind of a parallel approach, like I mentioned, to what we did in the prior sections. This time it's just all about predicates versus propositions. So let's give this all a try. Here we have a universal quantifier. Reading this out just in ordinary words, we'd say, for all x in the domain R, x squared minus 2 greater than or equal to 0. So we need to decide, is this true or is this false? Looks like some folks in class indicating looks like false on this one. I agree with everyone so far. This one looks like it's false. I can make that statement true by just eliminating the -2, but we cannot do that. We have to work with this predicate statement at face value. So this is the predicate, x squared minus 2 greater than 0. Pay very special attention to the domain of discourse because this is the part that matters the most. We want to determine if it's true or false. This one is false, but we now must show it's false. Really, this is trying to get us a little bit closer to some of the proof techniques that are coming up later on in the chapters. The way to show this whole statement is false is exhibit one counterexample. Because recall, a universal quantifier is true when every single one of these statements, there'd be infinitely many here because x comes from R, every single one of those has to be true, but we need to find one counterexample that makes this predicate P of x squared minus 2 greater than or equal to 0 false. So let's pick a value. Any value will do almost. Again, it has to come out as false, and sometimes it's true. I mean, plug 2 inside there, it's absolutely true. But let's say, for the counterexample, let's set x equals to 0. There's no reason to work too hard, right? If you set x to 0, then the predicate statement is p of x 0 minus 2 greater than or equal to 0, which is false. This tells us then, oh, let me make a correction here. This would be p evaluated at 0 gives us that statement, so that it tells us that p of 0 itself equals false. Then that finally tells us, with just the single counterexample, the whole original statement is overall false. Let's say, therefore, for all x in the set R, x squared minus 2 greater than or equal to 0 is false. And that's our answer. Let me box this out. I mean, we said it once already up here, but this is the explanation to go along with it. Any questions at all, folks, with coming up with the counterexample, or why the counterexample forced the whole thing false? Okay, maybe one major takeaway is that quantifier for all is really very, very restrictive. Anything that fails here, one thing that comes up false, no matter how minor, how small, means the whole statement was damaged all outright. It's just entirely false. But now there's a related statement or related concept to go along with this. That's why I boxed out the answer here. If the statement is false, the negation of that statement has to be true. It must be true. That's the law of excluded middle in logic. Things are only true, either true or false, nothing in between. So let's negate it just for the fun of it. This is good practice. Let's write out negation of the entire statement for all x in the domain of discourse R, we have a predicate x squared minus 2 greater than or equal to 0. This is truly De Morgan's laws working for us. Let's just state it over here. In this situation, think of the for all quantifier as being an and De Morgan's law says P and Q. Negation of that is logically equivalent to, didn't plan out the space here, let me just drop a line, not P, or, so we flip from and to or on this, not Q. So that's what De Morgan's law says for just two propositions, but this is a predicate statement, so there are infinitely many propositions truly, but it works just as well. So let's do this negation. We're going to get something logically equivalent to, notice how the and flips to an or. That's one of the major things to take a look at first. Just like over here, this one with the for all x is universal quantifier is just a lot of and statements. The existential quantifier is just a lot of or statements all chained together. So if we're negating something that has a lot of and statements, you go to loads of or statements, which implies immediately that's now an existential quantifier. So in the negation, the first thing that flips is for all becomes there exists, or at least one. So for at least one x in the set R, we have the statement that, well, not that statement there, right? We also have to negate these were propositions, we have to negate our predicate over here. So what's the negation of this thing? It's almost the same equation, but when you go to negate this, you need to be very careful with what's in the middle, that inequality operator. If it was an equality operator, you would just go to not equals. This one's a little bit trickier. Let me write out both sides. And what would you all say should go right here? Any volunteers for the right inequality?
You just flip it.
Close. You do definitely flip it. And one little extra thing as well. I forgot X right here. Apologies for the missing X. So it's going to flip directionalities. But anyone see what else would happen to it as well?
It also wouldn't have the equals, I believe.
Exactly. So when we go to change this around in a gate, it becomes strictly less than. Good call on that. If we include the proposition, let me say this a bit better. Greater than or equal to 0 includes 0 itself. But if we're negating that, we flip around the direction, and we're also, well, excluding the left-hand side this time is a way to think about that. So these are the two things that would change whenever we go to do a negation. We're going to practice this some more, but this is such new stuff to many people. I feel like we should practice it at just about every opportunity. Now, next thing that we should say here is that the prior one was false, but we negated it. This one is true. And yeah, there does really exists an X and R that would make this true. Pick X equals, say, 4, for example. You'll have 16 minus 2. That's not going to work. How about pick X equals 0 altogether? You'll have -2, strictly less than 0, making this a true statement. But for the existential quantifier, one true statement is all it takes to make the whole statement overall true. So this one was false because there's some values that make it false. The negation is automatically true, which means there is at least one value for X for which this should hold. And looking at a plot, we can see there's really infinitely many such values. Any last questions, folks, on getting through part A? We kind of beat it up quite a bit with the two things here.
Can you think of that statement as like the complement of the other one?
So this statement going down to this statement?
No, like there exists in this case would be a complement of the for all.
Yeah, absolutely. That's a great way to think about it. And looking at the inequalities as well, it's a kind of complement in at the same sort of time as well. When you say greater than or equal to 0, flip it out to less than 0. Those two sets of numbers would complement each other at that point. So lots of ways to think about these as being complement to each other. Any other questions or comments so far? Okay, let's try it out again then for part B. And I guess we have a part C coming up next. Part B says, determine if the following statement is true or false. There exists an element X in R, so R is now the domain of discourse, such that, this is the predicate statement, X squared equals 25. How do folks feel about this one? True or false? I heard true, absolutely. So this is true. We can think of a value X that would make that true, or you could just solve the equation. It's got to be 5. Well, keep in mind there's multiple solutions. -5 works as well, but is that relevant? Not really. If you find one value that makes it true, good enough. The whole thing is now overall true. So we'll say here, set X equal to 5. Then 5 squared equals 25 is true. That's enough right there. One true statement in an existential quantifier says, therefore, the whole statement for some X in a set R, X squared equals 25, is true. So one true example here is enough to make the whole thing true, but always view that statement with the opposite statement. One false statement here in the predicate is enough to make the entire quantified statement here false. In a certain sense, they're opposites. So we've got that this thing is true. Now we know if you were to negate that whole entire statement, it has to be patently false. There's just no other way to go about it. Because if something is true, its negation is automatically false. This just gives us an opportunity to practice negation, again, with the quantifiers. So let's give it a try. Go to that whole statement, throw a negation logical operator in front. We're negating the statement, there exists X in R such that x squared is 25. This becomes logically equivalent to same kind of game as what we did over here. Doesn't matter what the quantifier is, in its negation, it flips over. So for there exists right here, this becomes for all. We'll say for all x in the set R. So domain of discourse can't change. But what now must change is this right here. If you're going to negate an equation, x squared equals 25, not as touchy as the inequality. I would definitely want to get that one out of the way first. All you do is you go from here, drop in not equals to. That does it. So this is logically equivalent to the negation of this entire statement over here. And this statement here, well, we said this one is true and we negated it. This is false. Why false? Well, it's because it says for every x in R, it can't be equal to 25. But you know that's not true. There's a counterexample. There it is. Throw a 5 inside here, and this isn't true anymore. 5 squared is equal to 25. That one counterexample is enough to verify this is truly false overall. So it's kind of a weird game with quantifiers whenever you're dealing with the negation operator here. But any last questions, folks, on getting through that one? Okay, well, let's try this out again then. On a callback from an old problem back in the day, when we were all the way back in set theory, A subset B. Well, we want to express this whole definition now in terms of quantifiers. So let's actually recall some of that information. The tricky thing about the subset relationship is you can write in terms of quantifiers two different ways, depending on the context. So let's go way back to section 2.3. Let's just pull out that definition. This is out there on Moodle as well. I should have opened the PDF. These Word documents are a little laggy when there's so much digital ink on there, but we want to go for not quite set abstraction, but if you look really carefully at set abstraction, not too different at all with what we're doing here today. Our author makes a connection there in the reading, but we're looking for subsetting. So where is that? We're getting close. And closer. There it is, the subset definition. The thing that's touchy about this definition here is it's rolled together with the implication statement. And we know the implication statement, P implies Q, that on its own is very tricky. So let's be really careful when we go to work with this. So dropping it in, here's our definition from way back a few weeks ago. We say a set A is a subset of a set B, written A subset B. If for every x in A, it is also an element of B. But we work with this definition. One thing we don't quite have is a universe. It may not be relevant to us if all we're talking about is a subset, but if you wanted to do the complement of the set A, you need to say, what is the universe for this? So let's write this out first by considering a universe for our sets. Let U be the universe, or the universal set, for example. And I'm just going to scroll for just a second here. I want to tie together my color coding. My domain of discourse is yellow. So in set theory, the universe is going to turn into the domain of discourse when we go to write out our statement in terms of quantifiers. This being the universe means any set we write, all the elements from that set came from this universal set here. Now we can say A subset equals, oftentimes I just say A subset of B means this statement. Let's track it through the definition since we're essentially just retranslating it in our new set of logical operators and quantifiers. A is a subset of B, written this way, means for every x in A, let's start with that. For all x, and that looked weird. For all x going this way, for every x, I want to say for every x in the universe U. So this is the more general way to write out the actual subset relationship. We're including the universe, which is allowing us to take complements of the set A. For every element x in the set U, we have this statement. Notice it's an if-then statement. If x is an A, it's also an element of B, so we can write it this way. X, an element of A, implies X is an element of B. So this is the subset relationship written out in just formal logical operators and quantifiers. Every X an element U, determine first if it's in the set A. If it's in the set A, then it must be in the set B, as long as this is a true relationship. A is itself a subset of B. So we did it, folks. Sometimes this is kind of challenging, actually. One of the ones that's a little bit challenging is going to be going back to one-to-one, going back to onto, one-to-one functions and onto functions. We can translate in this way as well, but we need nested quantifiers. More than one quantifier is going to come up if you want to describe one-to-one and onto. That's really the whole essence of why those are tricky topics on their own. Just a lot more going on. But any questions at all, folks, getting to this statement here? Okay, well, our practice here was just trying to write things down in quantifiers or determining when the quantifiers are true or false. Parts in orange are not parts you would have to do as a homework question, just extra practice with negations. What we'll do next is start doing some translations. These are kind of silly in a way. The statements don't ever feel too important. Sometimes they seem just strange and contradictory. But the whole purpose of these kinds of problems is more practice, trying to make connections in our mind of what the symbols are trying to say versus these statements here. What would you say if you had to read this out using ordinary speech? Pretend you don't have any more pencils to write down things mathematically. You just have to say this stuff. Well, we have predicates to help us out. P is going to be the predicate. X is an ISU student. Q will be the predicate. X is a full-time student. The domain of discourse is kind of written in a weird way. All living people. We don't want to talk about people deceased. Weird to kind of say it that way because I think if you left this out, just totally deleted this part, it would have been clear what we're trying to say when we said X is an ISU student. We don't mean, well, we sometimes service dogs could get an honorary degree, but the spirit of the problem is we're thinking of X as being a human, right? So we didn't necessarily have to say that. Sometimes being hyper-specific is a good way to go as well. However, we're not always hyper-specific, so we'll see some examples that go like this. Notice in part C, sorry, I scrolled a little too far there. On part C, it just says for all X, doesn't mention the domain of discourse whatsoever. And that's allowed as long as the domain of discourse is clear through the context. If you always want to be very hyper-specific, not a bad idea to always define S and assert X comes from a set S. But down here, if we decide it's clear what X is, we don't necessarily have to state that part. Well, our goal is just to write these out in ordinary way. So pretty much you could do all these problems just going left to right, read out what the predicates are, and go from there. Let's say, doing part A, for all, well, we want to write out the statement in words. We should say for all X. We should say what X is. Let's say for all, I'll do living people just to be specific. For all living people, so we mentioned everyone in the domain of discourse S, it says P of X. So we just write out this statement. For all living people, the person, I'm saying the person in place of X is an ISU student. It's a silly statement, right? It's automatically false. We know it's false. I'm the counterexample. I am not an ISU student. I just work for ISU. I was once an ISU student, but not any longer. But if we just have to write out the statement, that's what it's saying. Any questions at all, folks, on getting through that one? These problems look like they go a little bit faster. Let's try out the next one. So for this part right here, how would you all start out the statement? Any volunteers for starting this one out, or the whole statement if you've got it in your head?
Is it saying for one living person?
Absolutely. Well, it's not necessarily saying for exactly one, but you're on the right track. It's saying for at least one living person. It could be exactly one, it could be 12, it could be 50, but the quantifier here is just saying for at least one. So let's
Okay.
say for at least one, or you could change this up and just say there exists a person. I'll go with the for at least one person. Then you notice I just said person this time. I didn't say living people. It's clear from the context what we mean by a person, what this domain of discourse S is. So if you wrote out like this to start, I'd say that's totally just fine. So that starts it out. Now we'll just look up the predicates P of X, Q of X, the connectives in the middle, and just read these out pretty much verbatim. We can say for at least one person, the person is an ISU student then coming down to this part right here, we'll say, and this person is not. So we have the and connective, the not connective from everything that's written out here. Then just read out what this says. The person is not a full-time student. And that's the whole expression. Does that make sense to folks on how we got from here down to just the ordinary words? Okay, well, certainly this has got to be true, right? There is at least one ISU person in existence that is not a full-time student. So this would make sense as being a true statement, but we're not too worried about the truth or falseness of this one. It's all just about practicing writing out the translation. So last one to go before we move on to the next topic. Let me hide example 5 down for the moment. This one's interesting because really there's lots of ways you could say this one. You could say it's not the case that for all people X, Q of X. I would think that's completely fine. You'd never lose credit for that. But the way I would probably want to attack this is slightly different. Let's actually do the negation and interpret the statement that we'll find it's logically equivalent to. So we'll begin by saying not, really just extra practice doing a negation here. Let me maintain brackets. Not because parentheses are bad, it'd just be weird to change formats. So negate for all X, Q of X. That would become logically equivalent to, this turns into an existential quantifier, at least one X, such that we also negate over here. So put in negation Q of X. That's what we were doing up above on those earlier problems when we flipped the, I think it was greater than or equal to a less than, when we flipped an equality to a not equals to. Essentially the same thing we're doing right over here. So the negation here gives us an existential from the universal and negates the predicate statement over here. I don't know if this is necessarily the easiest one to interpret, but at least we practice doing another negation. Let's read this one out. We can say, for at least one person, like we said before, but you've got options. Anything you say that captures the essence of what this is saying is totally fine. So we could turn this around by saying, there exists a person. So for that whole thing, that's just the bit right here, exist X. There exists a person. Here you could say for which, such that, any kind of conjunction here that would make sense. I don't know if conjunction is the right word. there exists a person, I'll go with such that. That's the colons that was right above. Not Q of X. So X is not a full-time student. Well, we have to be careful with that. We don't necessarily want to say the student is a part-time student, right? The negation of being a full-time student could mean not a student at all. There's lots of ways to satisfy the negation here. So I'll just say very carefully, such that it is not the case. That whole bit there is my negation operator, that the person is a full-time student. Let me fix that bit of penmanship there. Oh, we got it, folks. I lost that participant window for just a moment. Any questions at all on doing these kinds of translations here? Okay, well, we've done quite a bit of practice on this kind of stuff, but there's definitely more we want to take a look at. Going in one direction is usually easier with these kinds of translations. This is the easy direction when the logical formalized here and we just have to read it out. But if we start with the ordinary words like this kind of stuff, suddenly it feels a little bit more open to interpretation. So we have to be very, very careful going backwards now. So this is the problem where we want to take a little bit of extra time and be extremely careful with this. We're doing ordinary speech, and we have to capture the essence of what's being said here into a precise logical statement. First, let's take a look at our actual predicates. P of X is going to be X is an accountant, Q of X owns a Porsche. Looks like the domain of discourse would be you, all living people once again, but it looks like it's implied as well. We don't have any non-human accountants that I know of, excluding AI and that kind of stuff. So down here, we need to translate all accountants own Porsches. First thing we have to decide is, which is the right quantifier? Should we use this one or should we use this one? Any volunteers for which one to start? Look at the direction. It looks like some people are pointing for the existential. And I would agree. If you see an all here, sometimes that's a pretty good indication you're dealing with a universal quantifier for all. So from this portion here, this would be a good part to start. We'll say for all X. I'm leaving off the domain of discourse. We'll use the context to determine X is just some human that could potentially be an accountant, could potentially own a Porsche. So for all X, this is the tricky part. It says all accountants own Porsches. I want to give a couple options too. Here's a couple competing thoughts on this one. One thought is you could say P of X and Q of X. Another thought is you could say P of X implies Q of X, and only one of these is correct. There's only one right way to say this. Let's take a look at both of them and see which one it could be. What does this statement say? This would say for all people, the person is an accountant and owns a Porsche. And this one would say for all people, the person, if the person is an accountant, then the person owns a Porsche. Which one would you all say is more correct? Option 1 or option 2? We have option 2 from class. Anyone over Zoom have a strong opinion one way or another? Does it feel like option 2 or option 1 for folks in Zoom? Just noticing we have 1 minute. So we might have to wrap this up. It does turn out option 2 is the correct one. Good call on that. There's only one way to write this out, and it really is P of X implies Q of X. So what's wrong with the first statement? that says being an accountant and having a Porsche. But this is saying all people are simultaneously accountants and drive Porsches. That's a humongous, bold, overarching statement. This one is just an implication that says if the person is accountant, then the person owns a Porsche. Doesn't seem true either, but it's not as heavy-handed of a statement. It captures the essence of all accountants own Porsches, stating it as an implication. So going backwards again is pretty tricky. We'll practice this when we come back on. Oh geez, we're already done for the week. When we come back on Monday, we'll finish off this document here. And then in 3.5 feels like just more of the same, except the quantifiers are going to be nested. It can go for all X, exist X, that kind of stuff. But sorry for going right up to the minute. Any last questions, folks, before we call it a day? Okay, well, have a great night, folks. Drive safe out there if you're driving. It's supposed to start snowing, at least here in Idaho Falls. And see you all next week.
Thank you very much.
Yep, you bet. Take care. Yep, have a good one.
So funny here. My